In this video, we will explore set operations. By the end of this video, you will be able to complete the union of sets, perform the intersect operation, use the complement of a set, and find the difference between two sets. These operations involve manipulating and combining sets to create new sets with specific properties. The union operation involves combining elements from two or more sets to create a new set that contains all unique elements from the original sets. The goal of this session is to explore the process of finding the union of sets through various examples. We start by identifying the sets we want to find the union of. Let's denote them as set A, set B, set C. In step 2, we write down all the elements from each set, but we do it without repeating any. This ensures that the union set contains only unique elements from the original sets. Finally, in step 3, we collect all these unique elements from the sets. We write them inside curly braces to form the union set. Let's apply these steps to sets M and N. Set M contains apple, banana, grape, and set N contains grape, orange, pear. After combining elements and removing duplicates, the union of set M and set N is apple, banana, grape, orange, pear. And there you have it. We've successfully found the union of sets M and N. By following the steps outlined in this handout and practicing with examples, you can master the process of finding the union of sets. It's a fundamental skill in set theory and beyond. Why does this matter? Because understanding set operations like the union is crucial in various fields. It helps us solve mathematical problems and real-life challenges involving grouping, categorizing, and merging elements. To sum it up, set unions are not just a mathematical concept. They have practical applications. Mastering this skill equips you to tackle a wide range of problems more effectively. We're delving into the world of set operations, which are foundational in mathematics. These operations enable us to manipulate and analyze sets to discover new sets with distinct properties. This operation involves finding common elements shared by two or more sets. Understanding set operations, like intersection, extends beyond mathematics. The intersection of sets A and B, denoted as a B, is quite straightforward. It's simply the set that contains all elements that are common to both sets A and B. We start by identifying the sets we want to find the intersection of. We'll denote them as set A, set B, set C. Moving on to step 2, we examine the elements of both sets. Our goal is to identify any elements that appear in both sets. Finally, in step 3, we collect all the common elements we've identified. These common elements are written inside curly braces to form the intersection set. Let's begin by identifying the two sets we're working with, set A and set B. Set A contains 2, 4, 6, 8, 10, and set B contains 1, 2, 3, 4, 5. In step 1, we identify the sets we want to find the intersection of. Here, it's set A and set B. Moving on to step 2, we compare the elements in both sets. Our goal is to identify the elements that appear in both sets. Finally, in step 3, we collect the common elements. In this case, the common elements are 2 and 4. We write them inside curly braces to form the intersection set. So, the intersection of set A and set B is 2, 4. These are the elements that are shared between the two sets. Understanding set operations, such as intersection, goes beyond mathematics. It's crucial for solving various real-life problems, including data analysis, probability calculations, and more. Whether you're working on statistical research or analyzing datasets, the ability to find common elements between sets is a valuable skill. In summary, set intersection helps us identify shared elements efficiently, making it a vital concept in various mathematical and real-world scenarios. During this session, we'll explore the concept of set complement. We'll break down the steps to determine it and reinforce our understanding through examples. Understanding set operations, including the complement, is not just a theoretical exercise. These concepts have practical applications in data analysis, statistics, and more. The complement of set A, denoted as A, is a fundamental concept. It's the set that contains all elements from the universal set U that do not belong to set A. Think of it as the not A part of the universal set U. All the elements in U that aren't in set A make up the complement adding. The first step is to identify the universal set U. This set contains all the elements under consideration, and it serves as the reference point for finding the complement. In step 2, we identify the specific set A for which we want to find the complement. Set A is the set we're interested in, and we'll find the elements that are not part of it. In step 3, we closely examine the elements of both the universal set U and set A. Our goal is to identify the elements that are not present in set A. Finally, in step 4, we collect all these elements from the universal set U that do not belong to set A. We write them inside curly braces to form the complement set, denoted as A. First, let's look at the universal set, which we call U. This set contains all the possible numbers we are interested in: 1, 2, 3, 4, 5, and 6. Next, let's focus on set A. In this case, set A has the numbers 2, 4, and 6. In step 3, we compare the elements of the universal set U and set A. Our goal is to identify the elements that are not present in set A. Finally, in step 4, we use the elements we've identified in step 3 to form the complement set A. The complement of set A in relation to the universal set U is A equals 1, 3, 5. The complement of sets serves a vital purpose. It allows us to pinpoint elements excluded from a particular set in relation to a larger universal set. Understanding set complement isn't just theoretical. It has practical applications. These include probability calculations, data analysis, and set theory in mathematics. By following the steps outlined in this handout, you can confidently compute the complement of sets. This skill equips you to tackle problems across various fields and contexts. Set operations are fundamental for manipulating and exploring sets and their relationships. Our primary focus is on one of these essential set operations, finding the difference between two sets, denoted as A, B. The difference between two sets A and B, denoted as A, B, is a crucial concept. It's simply the set that contains all elements in set A, but not in set B. This operation reveals elements unique to set A when compared to set B. In step 1, we start by identifying the set A from which we want to find the difference. Set A is our primary focus, and we'll determine what makes it distinct from set B. Moving on to step 2, we identify the set B that we want to subtract from set A. Set B serves as the reference point for finding the unique elements in set A. In step 3, we closely examine the elements of both set A and set B. Our goal is to identify the elements that are only present in set A. Finally, in step 4, we use the elements we've identified in step 3 to form the difference as A, B. This set represents the elements that belong to set A but not to set B. In step 1, we identify set A set. A contains 1, 2, 3, 4, 5, and these are the elements we want to focus on. Next, in step 2, we determine set B. Set B contains 4, 5, 6, 7, 8, which are the elements we'll use for comparison. Armed with sets A and B, we can now proceed to find the difference between them. In step 3, we compare the elements of set A and set B. Our aim is to identify the elements that are exclusively in set A. Finally, in step 4, we use the elements we've identified in step 3 to form the different set A, B. This set represents the elements that belong to set A but not to set B. We've explored the concept of set difference today. This operation helps us pinpoint elements that are exclusive to one set but not the other. Understanding set differences is valuable. It allows us to identify elements unique to one set, which can be crucial in various mathematical contexts.